All right, we'll get started. Well, happy Friday, everybody, and happy New Year. And well, I don't know. How's everybody doing? It's week 6, end of week 6. We're doing okay. All right. Well, thank you to the 3 people who looked at me and smiled, and everyone else. I wanted to talk about the midterm. I know that's and we have an extended weekend. We have President's Day, so no class on Monday, and then Wednesday we'll have a midterm exam. And I'm still writing the exam, and so I'm not ready to tell you exactly what will be. I don't know if I should tell you exactly what will be on the exam, but I'm still writing it. But I will. I guess I will put something up that will kind of describe what you should study and how you can prepare for the midterm, and that will be that. I'll set up another seating chart and do something similar, and then we'll go from there. Okay? I mean, we've only really covered chapters 2 and 3, and parts of them at best. So I was going to I was debating what to do today with class, and looking at just how much time we have left in the quarter. I think I've got to kind of skip ahead a few things. Okay, so I want to. We started talking about the Bayesian approach for linear regression, and on Wednesday we did kind of like the grid approximation, kind of illustrating how we consider every single possible combination of the intercept and the slope when we're doing our analysis to get the posterior distribution. And that would be the grid approximation. And then what the textbook does is it kind of does an analytic approach using the conjugate prior, and it gives you kind of a maybe almost a closed form solution of what the posterior distribution will look like. Okay, and then we are going to skip chapter 4 in the textbook. And I'm going to, next quarter, if you are taking 102C, we will look not at chapter 4, but the topics that covered, which is going to be kind of Monte Carlo sampling of the posterior distribution. So I guess I'll just talk very briefly about it so you have an idea of what next quarter is kind of about. But so in our, what I did not yesterday, on Wednesday, was we did the grid approximation for every single possible combination of slope and intercept, right? And there we had basically a slope term and an intercept term, and maybe I had, if I did a grid of 100 by 100, I would have 10,000 locations to check, right? And for a lot of them, those locations, the likelihood ended up being 0 or something, on the order of 0, and the distribution only existed in certain areas. You could imagine that if I had, polynomial regression with 7 coefficients, and I wanted to do a grid of 100, it would be 100 by 100 by 100, 100 to the 7th power, and that's like way more combinations to consider, because in the Bayesian analysis, we would have to consider every single possible one of these. And then, and having that many would kind of bring your computer to its knees. And so what we do next quarter is we do some Monte Carlo methods. Okay, so these are just basically computational methods that allow us to get to sample from that distribution without having to do every single possibility next quarter, okay? But we did at least cover the basics of Bayesian analysis, in that we said, you have a prior distribution, you have a likelihood, you have this normalizing constant on the bottom, which we call the marginal, and then you get the posterior when you combine all of them. I'm going to go ahead and skip ahead to chapter 5, and chapter 5 in the text is on classification. Was that? Yeah. Will I cover classification on the midterm? No. I will not put... I'm going to start classification today, but I will not cover classification on the midterm, okay? So chapters 2 and 3 will be covered on the midterm, and trying to figure out the problems to write, okay? So, and figure out the appropriate length and appropriate difficulty, and, you know, it's a challenge. It's a challenge. Okay. For me to write the exam, not like I'm not trying to make a, well, whatever. Okay. So, okay. So classification. You know, we've already covered a classification method. That was the neural network that was used to classify our digits into 0 through 9, or classify the iris data into one of the 3 species. But, you know, in classification in general, the idea is you've got your data, which is going to consist of some values of x. So you've got x1 and x2, and these are all vectors, okay? Multiple values, right? So each x is a vector in d-dimensional real space, okay? And then the output will be some classification, you know, T1, T2, T3, all the way through T sub n, where T sub I is going to be an element of some something, right? You've got some set of C possible classes. Okay, and so the neural network could be used for regression, but we saw neural network for classification. Right? You had the digits. Each x was 28 by 28. 784 was a vector of 784 values. And T was something from 0 through 9. Okay. And then you also had the iris, and each x was 4 columns, right? It was a vector of 4 values. Petal width and length and sepal, whatever. And then, you know, you had three species. Class was one of 3 species. Okay, and so that's what we have. I think you have covered in another class, what, 100C? Or is it 101A? Logistic regression? Where do you guys do logistic regression? Huh? 101A. A little bit, right? So basically, logistic regression is just linear regression, but you throw it into a logit, right? Okay, so logistic regression also counts as a classifier, but it only works for 2 categories, right? For a yes or no, right? So the input is a vector of x, and the output is a probability of, I guess, t equaling 1 versus t equals 0. Something like that, right? It's the worst picture ever, but... Okay. Today, I'm going to introduce something called the Bayes classifier, okay? The Bayes classifier, as much as it sounds like it's a Bayesian thing, it's not really Bayesian. It uses Bayes' rule, and that's why we call it Bayes classifier, but it's not Bayesian in that our parameters are not coming from distributions, okay? It uses Bayes' rule. Yeah, you could have a Bayesian Bayes classifier where you consider everything to be a distribution, but that's not the case here. Okay. All right, so let me introduce the Bayes classifier. This is a probabilistic classifier. Probabilistic classifier. And what that means is that the output of our classifier, the output is a probability that the observation belongs to a particular class. Okay, so logistic regression is a probabilistic classifier. So that counts. Okay, and so we might just say the output is going to be the probability okay, so this is the probability that the random variable t, which is the class for our new observation, okay? So this is the probability that our new observation belongs to class C, okay? And over here is given dot 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 the x values of our new observation. And the existing training data, which consists of x and t. So this is what we are going to output, right? And if I sum the probability of t new equaling class C, given x new and x and t, if I sum this across all values of C equals 1 to, I don't know what the, I don't know, k, right? So for all possible classes, what would this add up to be? It would add up to 1, right? So, for example, what is, it would be like the probability that x new is, what is it? Setosa, given, the data. Maybe this is 0.10, and the probability that x new is, what are the other ones? Virginica. And given the data, maybe this one is 0.85, and then I don't remember what the last one was. What was it? Okay. Huh? Versicolor. There you go. All right. One day, I'm going to meet somebody who's a fan of irises, and then I will say, oh yeah, my favorite is. And they will be like, wow, you know a lot about irises. Clearly. Okay, and then so, the result of your classification is going to be something like this, right? You're going to get, what's the probability? After you run it through this, you put the data in, it's going to spit out, I guess, a vector of 3 values, right? And it's going to say it's going to be Setosa, probability 10%, Virginica 85%, and Versicolor with probability 5% or something. I'm just completely making this up. But the total probability has to add up to 1 in this case. All right, does this kind of make sense? This is what we are aiming for, right? Okay, so to get this, we're going to use Bayes' rule, okay? So this is why we call it the Bayes classifier. Okay, so we use Bayes' rule, our very favorite. So we're going to say the probability that T new is equal to class C given our vector x new and x and T. Okay, this is going to be the probability of x new given that T new is class C and our x and our T, okay, times the probability that T new equals class C given our x and our T. Does that fit? Okay, good. And then we divide this by the probability of x new given x and T. All right, what does this translate to? So let me just kind of write. Okay. All right, so this is, so I just applied Bayes' rule, and I just switched the terms x new and T new, basically, right? Okay, let's parse this out. Okay, this first term, this is going to be our likelihood term. What is this? This is the probability of getting the values in x new if the classification were class C, okay? If the class is C, okay? So what is the probability of getting the values in x new if the class is class C multiplied by the prior probability that a random observation belongs to class C. And then this would just be divided by the probability of getting the values x new given our training data. So we ask, what's the probability of getting the values in X new if we know that the class is from class C? Okay, and this bottom term, the bottom term, probability of X new, this is just a normalizing constant, okay? Basically, it's just going to be the sum of the numerator, so that when we do this, the whole thing adds up to 1. Okay, so if you calculate the numerator terms, and your numerator terms are like 0.01, 0.08, and 0.01, okay, all of those things add up to 0.1, okay? And so the normalizing constant on the bottom would be 0.1, so that everything gets adjusted in the numerator to be 0.1, 0.8, and 0.1, so that the whole thing adds up to 1. Okay, so that's all it is. Okay, so really this is just the sum of the terms, the numerator across all classes of C. So we could say this is the sum of probability of X new. We don't have to write this, but okay. So the probability of X, just copy the numerator. For real. That's exactly what I'm doing here. Okay. But you sum it across all values of C. That's what this is doing. So we can obey the rule that our probabilities have to add up to 1. Okay. All right. So let's start off with like the easy thing. Okay. Probability. Well, I don't know if this is easy, but let's look at the prior term. So sorry, I should label this. This is the likelihood, and over here this is the prior, right? And down here this is our marginal. Okay, so the prior term, this is the probability that some random observation belongs to class C given our training data, right? So this is probability that a new random observation belongs to class C, okay, prior to us looking at the data. All right, so there's all sorts of things, like the prior distribution could be, prior to us looking at the data in X new, I should say. Okay, so this is the prior that T, some new random observation belongs to class C given our training data X and T, okay? So what probably makes most sense, okay, so a sensible choice of a prior for the prior would be basically the number of observations in class C divided by the total number of observations. Okay, so you'd have So what's the probability that some random observation is Virginica? Well, you'd say, well, in our training data, I don't know, 40% of observations are of class Virginica. So based on our training data, when I pick a random point in the future, I'm going to guess there's a 40% chance that it's Virginica, okay? Or maybe the training data, I think the training data was like evenly split. But who knows, right? So that's a sensible choice, okay? Other options is you could say, well, maybe you didn't bother counting. You can just say, well, just do 1 over the number of classes, right? So if you have 5 classes, this is 1 over number of classes. This would be the kind of the uninformative prior. This just assumes all classes are equally likely. I guess this one, what would this assume? This assumes the training data is representative of the population, right? You've got to make some kind of assumption at some point. So either you have to assume that all classes are equally likely, maybe that's a good or bad assumption, or maybe you have to say, I'm going to assume that the training data I have is representative of the population. That may or may not be a good assumption. Or you can just say, I think class A has probability 80% because I am knowledgeable in this field and I'm going to use that. And that's fine, right? If you say, well, I'm confident in my knowledge, go for it, okay? Just other options, something not arbitrary, but something else based on your, quote, expert knowledge. So you might say, based on past data or whatever, I'm inclined to believe that, I don't know, 30% of UCLA students, whatever, something, okay? So that's all, right? So this is the prior term. This is just before you look at the values in X new, you just say, well, based on my training data or based on whatever else, I'm going to say this is the prior probability that some random observation belongs to class Virginica, class versicolor, class setosa, or whatever. Okay, so this will in R will be represented by a vector of values with a value for each class. Okay, and that vector will have to add up to 1. Okay, so in R it will be represented by a vector of length, number of classes that sums to 1. Because this itself is a probability distribution, so it has to sum to 1. Okay, so that's the prior term. And then, let's talk about the likelihood term, or we might call this the class conditional term. Class conditional. Okay, so then we'll say the probability of getting our value x nu given t sub nu is equal to c given our x and our training data, okay? And this is basically the probability of getting our observed value of x nu if the class was class C. Okay. And so of course you're going to have a different one of these for each classification. So you have to figure out the probability for each classification. These things will not necessarily add up to 1. Okay, they could add up to something, you know, much smaller, or just something different, because here we are just considering all possible classes, and that doesn't necessarily have to be the case. Okay. So this, you'll need to specify some kind of distribution, okay? So if x is, I guess I'm assuming x is some kind of numeric variable, right? So we will need to specify, but I suppose it could be categorical also. We will need to specify some kind of distribution distribution on x, okay? On x for each classification, for each class, okay? Okay, and so, you know, you have all sorts of choices, but if you have, I don't know, 2 numeric variables, maybe you will choose like a multivariate Gaussian. That's like a possible choice. Okay, so you have, you know, of course, many choices, but popular ones. Multivariate Gaussian, but you could have, I don't know, multivariate beta or whatever, you know, or just some kind of product of things, right? Is the multivariate Gaussian, and you might, if we do something called the naive Bayes classifier, what we end up doing is we just say things are products of each other. Okay, let me just demonstrate. We'll try a numeric example, and I hope this will kind of make sense. And yes.
So when you say like when you specify distribution on x each class,
yes.
Do you mean like for different classes you might have different distributions, or like the same one for every?
You're going to have different distributions for each class. Yes. Okay. So each class will have a different distribution. Yeah, some kind of distribution on x for each class. Yeah, so each class has a different distribution of x. Okay, so I'll try to, we'll try an example here. So imagine some bizarre scenario where this is like the worst. Okay, Okay. All right, let's say, what's a department at the school that is, has more of one gender than another? Huh? English? Oh, okay. I was gonna just say like engineering or something, right? And I'm very thankful that in statistics we are probably among the physical sciences, we're one of the most evenly, like we're almost 50% male and female in the statistics department. But the same cannot be said about like electrical engineering. There's still a great discrepancy. But okay, let's just pretend for some department, let's say it is, I don't know, 80% male. And just for simplicity, I'm going to just use two genders. And I know it's not this simple, but just for the purpose of this illustration, we will just say, we'll say 80% male and 20% female. Just so to make our calculations easier. Okay, so let's say this, and then let's say, I don't know, you get a piece of paper, and this is a randomly chosen student. Okay, so we get a random student, and we are going to try to guess the student's gender based on their height and weight. So for whatever reason, I don't know, on this application we have height and weight numbers, but we don't have any other information. And based on this, we're going to try to guess the student. Okay, so this is just a terrible thing, but I'm hoping it's illustrative of what we're trying to do. All right, so we get a random student. We have this person's weight and height. Okay, and we want to guess the student's sex. Okay. All right. So what we have to do is, so based on our training data, we create our different class conditionals. Okay. So x new is a vector of two values, right? Weight and height. We create our different class conditionals. Okay, and so this part where we create our different class conditional distributions, for our example, we are going to do just maximum likelihood estimation. It is not Bayesian. You could do a Bayesian approach for this, but we're going to just use maximum likelihood estimation. So basically what this will look like is we have our training data, right? And we will split it. And we'll do, we will split into males and females. And we, and based on this, we will create some kind of distribution, right? So maybe we're going to say height and weight follow a multivariate normal distribution. They don't, okay? Height follows the normal distribution. Weight is not quite normal. It's generally right skewed. But for simplicity, we'll just say height and weight follow a multivariate normal distribution. Is that okay? So we will assume the joint distribution, the probability for the distribution for weight and height come from basically a normal distribution. And so, your maximum likelihood estimates will be the mean weight and the mean height, and then the variance-covariance matrix of your data, right? And so what we will end up having is our class conditional based on our data, and I'm making this up, will be something like we'll say for males, our joint distribution, the probability, I'm going to just write probability of weight and height, I guess weight and height given T sub n equals male. This will be a normal distribution where the mean is equal to, what's the mean weight? 165 and mean height 70. I don't know. I'm just making stuff up. Okay, and then some joint, some variance covariance matrix. What's the variance of weight? We'll say, 25 squared, and the variance on height will be, 3 squared, and some covariance. What's the covariance between? I don't know. Okay, some number here, right? We'll just put in a covariance term and covariance term. Okay, we'll say that. All right. So this is our distribution for the weight and height for males. Okay, and then we do the same thing, but for females. Okay. All right, and again, recognizing that we have simplified life by saying only two classes, but okay, and so then we'll have a normal distribution where the mean, 135 and 65, I don't know, I'm making stuff up again, and 25, so covariance, and 2.5, I don't know. Okay, so this is just based on your training data, right? So we have a distribution for the males, and we have a distribution for the females, right? And here I chose to use a multivariate normal. You may choose to use something different, okay? But now we have a distribution for each one. The prior distribution will just be this. So let me just copy this. I don't want to rewrite all of this. Oh, shoot. Okay, so these are our class conditionals, or these define our likelihood terms, and then the prior distributions will be just based on our knowledge of the department. This will be probability of male is going to be equal to 80%, and probability of female is equal to 20%, right? And then, okay. So this is all the information we need, and then so now we have our random student whose height and weight we know. Random student has height equal to, we'll say has weight equal to 140 and height equal to 65. And so the question is, based on this knowledge, the weight and the height, would you guess that this person is male or female, right? And the answer, well, right now, we have no idea, right? Because there's a bit of a balance, right? If we go straight off of the weight and height, and we go off the class conditionals, these numbers are more closely aligned with numbers for a female, right? However, our knowledge about the department says the person, if we just pick someone at random, the person is more likely to be male. So we have to kind of balance these two, and so we basically just multiply them together, okay, to get some kind of number. So okay, so do you guess? And of course, this is just a guess, and the real right, the real person has a specified gender, or sex, or something. All right. So do you guess male or female? Right. All right. Okay. So so what we have to do is we say, okay, well, what is the probability of male? Okay, and so this will be the probability of getting the values 140 and 65 if class is equal to male times the prior probability of being male. Okay, so this part, requires the multivariate normal density or multivariate Gaussian density. So this is the same as d norm, except, oh man, it's already 450. All right, we would do dmv norm. So in R, we would say, what is the probability from the multivariate normal of getting, and we would put in the vector 140, 65, and then all of this stuff, right? Comma, mean equals 165 and 70, and variance is equal to the matrix, right? And then the prior, and we multiply this times 0.8. That was the prior probability. Okay, so this is numerator for male. Numerator for male. And we do basically the same thing, but for female. We come up with a numerator for female. And then those two numbers will not add up to 1, but we add those two together to get what we consider our marginal, and then we basically just scale everything up so that the two things add up to 1. And that would be your answer to this. I don't know if that kind of makes sense. We'll look at this again on, oh, it's going to be Friday? That's the next time we actually have a lecture? Darn. Okay, well, maybe I'll post up some text or a file for you to explore. Okay, we'll end here. I will post up some information about the midterm exam so you guys can study this weekend and stuff. Have a great holiday weekend, and we'll see you guys on Wednesday.